today we're going to get to sections 4.1 and we'll see how much of 4.2. So this whole chapter is on probability, right? And we're going to be looking at the basic concepts and the addition and multiplication rule, right? The other section, there are 5 sections. The last section we will not be doing, so that's why it's crossed off here. This third section we will do, but we will not do the part about Bayes' theorem. Bayes' theorem is kind of, I've taught it before in a different class that I've taught, but it's kind of an involved thing, right? And the book does not adequately address it. So it's very confusing, and the book gives like half a page to it. So I don't think it would be fair for us to spend any time on it and for me to assess it. So that section instead will just mostly cover complements and conditional probability. The important part being this. Okay, basic concepts of probability, right? So this section, again, I apologize, is going to be a little bit boring, right? Because again, it is, and a lot of these sections are, because it's just giving you basic tools, right? Things that you will actually work on that will be interesting, kind of come in later sections, right? So we're mainly going to focus on, right, some definitions, right? You're going to find the sample space of something, and then we're going to work on theoretical probabilities mostly, and a little bit on experimental probabilities. So let's just give you some primitive terms. These aren't necessarily some of the best definitions because, right, like primitive terms, like how would you define number to somebody, right? Like sometimes they're hard. But an event is any collection or result of an outcome of a procedure, right? Don't worry about the definition of these things. A simple event is one that can't be broken down into smaller components, right? So an example could be, right, rolling, you know, in each board game you play, you usually roll 2 dice, right? So rolling a 7 could be an event, but it's not a simple event because it could be done in different ways, right? You could roll a 3 and a 4, right? Or you could roll a 4 and a 3. That's actually different because they're 2 different dice. You could roll a 1 and a 6, right? So a simple event would be something that could only happen in one way. The sample space consists of all possible simple events, right? And you'll see an example. So I don't focus on the definitions. It's mostly the intuition of it. So what's a random experiment, right? You can kind of think of something that's random. It's something that I could do that has varying results, right? So if I put a sock in my drawer and I open that drawer, not really a random experiment, right? We know what's going to happen when I open that drawer. So we're thinking about things like these, right? Just these are a lot of gamified ones. There are more other ones. The other one is you wake up tomorrow and you see, is it raining or is it not, right? That's also an idea of a random experiment. So your sample space is simply the list of all possible events, and you typically put them inside these brackets like it's a set, right? So it is the list of all simple events. So if I roll 1 dice, there are 6 possible outcomes, right? So that'd be my sample space for the experiment roll a dice. Flip a coin, my sample space would be tails, heads. I mean, order doesn't matter. It would be very bizarre if you put the numbers from 1 to 6 in any other order, but you can't. All right, we good on all the definitions. Just stop me anytime that I say something you guys don't follow, because a lot of this is just pulling definitions out. Not the most exciting. So here's a more interesting experiment, or still not, but it's pretty simple. There's more than one thing going on here. I'm flipping a coin and rolling a dice at the same time. So how many different possible outcomes are there? So let's think about it. How many ways could the coin go, everybody? And right, that would be my heads and my tails. Now, do heads and tails like preclude me rolling any particular numbers. So for whether I get heads or tails, there are 6 outcomes for the dice. That's a total of 12, right? I could get a heads and a 1, a heads and a 2, heads and a 3. I'm not going to say the rest of it out loud. You get the picture, right? So this sample space would have 12 possible outcomes, and you can find your different ways to abbreviate them. So I could write heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, T1, T2, T3. So if I said, right, and I will do this, right, we kind of get in this, students forget by the time we get to the end of this unit what a sample space is, how to write a sample space. You simply write all the possible outcomes. It's fairly straightforward. So the sample space is all the simple events, right? But you could describe something else, right? So these are some sample spaces, but an event might just consist of part of a sample space, right? So for example, in this thing, rolling a 6-sided dice, right? The sample space has 6 outcomes. The dice shows an even number. That is an event, but it's not a simple event. But you can specify this event by telling you all the simple events that consist of that event, right? So for example, this event consists of 3 simple events or 3 outcomes, same thing. This event 2, dice shows a 1. Is that a simple event or not, class? Everybody, this is easy. Dice shows a 1. Is that a simple event? Are there multiple ways for this to happen or exactly one? Just one. So this is a simple event. It's made up of one outcome, right? This is a compound event or just an event, right? Here are some other ways to write events, okay? All right, so just to get you guys not completely bored, and it is a little warm in here, so maybe I'll open a window a little bit more, right? So a couple has 3 children, right? You know, there are intersex people, and you know, gender is a spectrum, but we're just gonna, most people are at one or other end. So to simplify this, we'll just say that every child is either a male or a female at birth, right? So let's just simplify that as far as this. And if you're having trouble, think about the order, right? So many of you might be in large families, right? It is a different event if 2 males are born and then a female, right? That's a different event than a female and then 2 males, even though the number of males is the same in each event, right? So try to answer both of these questions, right? So draw the sample space, right? And then list all these single events that make up the event, more girls than boys. Does everyone understand what they're being asked to do here? So I can start. So here's the sample space. We can use boys. So you could have all boys. So B, B, B. That's a boy is born, a boy is born, a boy is born. Or you could have B, B, etc. Right? Does everyone understand what they're being asked to do? Some of these, and neither of these would be part of this event here, right? So you have to figure that out after you do that. So let's all do this while I open some windows, try to cool it down in here, and take attendance. All right, this shouldn't have been too hard. So what are some of the other ones that we have? Let's see, I got boy, girl, boy, boy, girl, what else? Yeah, go ahead. Be more specific. Yes, but the order matters. So is this, so I think you're thinking girl, girl, right? But there would also be girl, boy, girl, right? And then, so what you described is actually 3 separate outcomes, right? You got to be careful about these. Then there are somebody else. I think there are 3 more. What else got? Yeah, probably. Yeah, all right. Anyone else see any that are missing? Yeah, that one I think you have there. Yeah, anyone, and I think there's one more. Girl, boy, I don't think is on. Yeah, it's hard to do that because I kind of use 3 people's different organizational ways at the same time, right? If you think about this, if I drew a tree diagram, we'll do this with the counting. There's 2 choices for each child. So 2 times 2 times 2 is 8. So that helps us figure out how many there should be there. All right, so more girls than boys. So you can kind of just look at each of these, right? So why it's nice to have a sample space is you can easily, right, find out all the events by just categorizing it, whether it's part of an event or not, right? Each outcome. So these are all the outcomes. So we can just do a checklist, right? So let's look here. What are some outcomes that are more girls than boys, right? So here's one. What about the next one? Yeah, and then girl, boy. And so there are a total of 4 such outcomes, right? See highlighted. And there are 4 out of 8. So the probability is 4/8 or 1/2, and we'll go through all the other ways. You could write this as 0.5 or 50%, right? Notice it's important for you to break things down into the simplest events, right? So maybe if I had just listed 2 girls, 1 boy as one event, right, I may have miscounted this, right? I would have said, actually, if I miscounted everything that way, I would have been lucky and got the same probability, but you have to break things down, right? So a lot of times, like if I say roll 2 dice, right, rolling a 3 and a 4 is different than rolling a 4 and a 3, even if they're simultaneous, right? Imagine one dice is green, the other one is red, right? Or if they're not, there's something about one of those dice that's different than the other one, right? You have to consider all the possibilities. Okay, so what we just did was calculate a theoretical probability. And we'll see what it means. So the probability of an event, right, is the measurement, right? Again, this is kind of a primitive idea, but we all basically get it. It's the likelihood or event or chance will occur, right? Here's something that's very important. Probability is a number that is between 0 and 1, 0 and 1 included, right? We will learn formulas for calculating a probability in this class later today and just later, right? And some of them will get complicated. You will make mistakes. But your answer never, ever, ever should be negative or more than 1. Okay? That is nonsensical, and you understand why. So just please sear that into your mind, right? I don't want to see, I know it will happen. It's happened every single time I've taught a class with probability. A probability that is not between 0 and 1 as an answer on anything I ever give you, because you know that's wrong. You get an answer like that, try again, right? Why is that? Well, we'll find that out in a little bit. And as we did on the last slide, you can express these as a decimal, as a percent, as a fraction, or as a reduced fraction, right? And typically, you can use the symbol P parentheses, right, where the parentheses go around the event, right? So if I write something like P heads, that means probability of heads equals 1/2. Here's why. Probabilities, the larger a number is, the more likely an event is to occur, right? An event that has a probability of 0 is an event that is not going to happen, right? If I have a bag of all red marbles, the probability of drawing a blue marble is 0 or 0%. Probability of drawing a red marble, assuming I'm actually drawing the marble, right? That is certain. That is 100%, or a probability of 1. A probability of 2 or 1.5 or something would be more likely than certain. That just doesn't make any goddamn sense, right? That's absurd. So a probability formula will never give you an answer more than 1. If it is, you did something wrong, right? How can something be 50% more likely than certain, right? Or 20 times more likely than certain? That doesn't make any sense. Likewise, a negative probability would mean it's less likely than impossible to happen. Again, you can't even imagine what that is. It's just nonsensical to even say it out loud. So you should never get a number like that. You also see why you should never get a number from the formula that's coming up here. So like look at what we had before, right? We listed the sample space. To show it, right? This is the example I have you do. You have 8 things in your sample space, right? There are 8 outcomes. A sample space is best if all outcomes are equally likely. In this case, they are. That's why we have to specify different orders mean different things. Because otherwise, certain things are more likely than others, right? There are 8 events, each equally likely. The event that we specified has 4 outcomes that make up that event, right? So we would call those 4 outcomes favorable outcomes. Right? So notice probability is number of favorable outcomes divided by number of total outcomes. So before, there were 4 such outcomes that involved having more girls than boys, and there were 8 outcomes total. So that gave us 1/2. Could you ever have more favorable outcomes than total outcomes, class? No, right? That's just what the word total means. So the number on the bottom of this fraction has to be larger than the number on top of it. So again, this as a fraction cannot be more than 1, right? Again, neither of these numbers could be negative either, so this ratio also has to be more than 0. All right? Pretty straightforward. You guys know this, you guys get this, but at some point in time, you're just not going to be thinking about it. And somebody in here, I know, will give me an answer that doesn't make any sense. All right, so let's take a look at this. This is the strategy you follow for everything, right? So Tyler's taking a quiz, and he doesn't know, or he's just randomly guessing for 4 of the questions, right? And it's a true false. So we want to find the probability of getting exactly 2 correct. So the way you want to do this is write all possible outcomes, and then see how many of those outcomes show exactly 2 correct. So let's just kind of go through this. And we'll do it, all right, to kind of give us some more structure than I did before. We will write them all out. So this one's pretty easy. There's only one way to get 4 wrong answers or 0 correct answers. That would be everybody. All wrong. So W, 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 W. All right. How many ways would there be to get 1 correct answer? 4, right? Either the first one, second one, the third one, or the fourth one. See if you can do 2, and you can try 3 and 4 are not very difficult, right? So try to do 2, though. It's easiest if you write it down. see. Got some. Let's see here. I'm sure you got quite a few. All right. Let's just see. Anybody got at least 3 outcomes? How about anyone got 4? 5, 6. 6 is correct. Let's go through all of them. Everyone get these 6. Yeah. All right. Now the other ones are easy because notice 3 correct is the same thing as getting 1 wrong. So you can just think of it as instead of placing that C in 4 different spots, I'm placing that W in 4 spots. And of course, there is only one way to get all 4 correct, right? So this is a total of how many ways? Yeah. There are 16. We could have also known that because there are 2 possibilities for each question. 2 times 2 is 4, times 2 is 8, times 2 is 16. We will formalize this counting method later. We were trying to figure out the probability of getting exactly 2 correct. So how many of these outcomes are favorable? So how many of them involve getting exactly 2 correct? Now, perhaps if you're Tyler, you would prefer getting more than 2 correct. So favorable does not mean like literally, as in it is something that I would like to occur. It just means an event that makes up the, outcomes that make up the compound event. So there are 6 favorable outcomes, right? Out of 16 total outcomes. So the probability of getting exactly 2 correct, see the notation I'm using there, is 6 out of 16, which reduces to 3 out of 8, which you can write as a percentage. Or as a decimal. Now, has anyone ever heard of the phrase complementary colors? Does anyone know some of the complementary colors or like how to find one? Let's see, has anyone been in art class? Okay. Well, who knows their primary colors? Yeah. Red, blue, and green. I know I didn't say those in the order I wrote them, but it's all good, right? Yellow. Yellow is the primary color, right? Okay, now there are some famous color schemes often make complementary colors, right? Holidays, sports teams. Anyone have a favorite sports team they want to say? Let's see, I didn't hear. The Bears? What are the Bears colors? Blue and orange. How do you make orange? So this is orange, right? So the Bears colors, the orange and red and blue together are considered complementary colors because together they make up all 3, right? They have blue's complementary color is orange because it is everything other than blue, right? So this is what so think about that word with complementary colors. So complementary events take all the outcomes, right? So notice here to make orange, it's the complementary color of blue because you take everything that's not blue and put it together. So the probability that if I choose some event in the sample space, some outcome in the sample space is 1, right? The total probability is always 1. So the complement is basically the opposite of the event, right? So if the probability, if A is that it is raining, or let's be a little more specifically. Let's let A be the event that sometime tomorrow at this, right outside this window, it rains. The complement of that would be all of tomorrow, it never rains on some whatever spot I'm choosing, right? So if the probability, roughly speaking, of rain is 30%, the probability of not rain is 70%, right? So to get 1, or if it's 30% as a decimal, 0.3, 1 minus 0.3 is 0.7, right? So the probability of a complement is just 1 minus the probability of the event, right? You can read this symbol as a bar. You might also see something like this, right? That could also mean. So you can also read this as probability of not A, or probability of A bar, or probability of complement A. Sometimes it is easier to compute certain events indirectly by calculating their complement, right? So here's what I'm talking about, right? Here is how you play most board games, right? That involve dice. You roll 2 dice, right? Like in Monopoly, you move your little top hat or your car or the clothes iron, whatever. You move that piece that many spots, right? Notice that the dice, right, even if they are actually the same color, they're 2 separate physical dice, right? So getting a 5 on the first dice and 6 on the second is different than getting 6 on the first dice, 5 on the second, right? So if I wanted to calculate the probability, right, that the sum is not 6, this would be, I guess it's not hard, but it would take a little while to do directly because there are a lot of ways that that can happen. But this is the complement of an event, right? I'm trying to find the probability that the sum is not equal to 6. What's the opposite of the sum not equaling 6? So I could if I can find out that probability, subtract it from 1, that'll be faster. Let's figure that out. Well, how many total outcomes are there in this grid? All right, let's see how many of them add up to. So 1, 2, 3, 4, 5 outcomes add up to 6. So, right, and we'll have more complicated ones. Some events, right, sometimes the strategy you want to use is complement the probability of the opposite occurring and then just subtract that bad boy from 1, right? That's a valid strategy a lot of times if one event's more easy to calculate directly. Perhaps this strategy, this is a small example of it. Perhaps you can't see when you would use this strategy, but we're going to be doing a lot more interesting things than this. Again, same thing here. Here the sum is less than or equal to 9. That's most of the things in this table, right? The easier things to count would be the opposite, which would be the sum is more than, you could say the probability that the sum is more than 9, or you could say is more than or equal to 10, right? One thing you want to be careful is when you do complements that involve or equal to, you have to leave it out when you flip that over, right? Because sum being less than or equal to 9 is not the opposite of being more than or equal to 9, because notice being equal to 9 would be in both of those compound events. You guys feel me on that one, right? So let's look at this. If it's going to be more than 9, the smallest it could be is 10. I see 3 possibilities for 10, 2 for 11, and 1 for 12, right? So this would be which reduces to 5 out of 6. Any questions here? This should be fairly straightforward. Not this, no, nothing. This is chapter 4. But yes, you will be assessed on this at some point. But yeah, this will be on celebration number 2. So empirical or relative frequency-based probability, right? So with these sorts of things, you can calculate the probability from mathematical reasoning, right? You can't really do that when you are, if I try to tell you the probability of rain tomorrow, right? So when you're looking at the probability just based on, like, if you had to do that, right, you might just do an event many times, right? And then it's just the number of successful trials out of total trials. So this is one that's, the formula is the same, except it's trials as opposed to possible outcomes, right? So I should probably change this result, but I've just been lazy. I've been using it for years. Imagine that there's a world where all adults, well, you're only allowed to have one pet, I guess. That's what this example assumes, which is kind of weird, but let's just roll with it, right? So, okay, let's say this is the study you do. You talk to, and notice they're only talking to people who have pets, right? You ask people, what type of pet do you have? Or maybe, since people can have different kinds, what type of pet did you buy most recently? I mean, if you buy a cat and a dog at the same time, that's kind of weird. So that didn't happen. So you got 16, say 916 bought a dog, 677 bought a cat, and then fewer people bought a fish and a bird, right? Well, here's the total. And if we want to do dog, the success is 916. So we can say that this probability is 1 out of 2, right? It's not necessarily exactly the probability that a person has a dog, but by doing trials, just finding random adults, right, 1/2 of them had a dog, right? So this is an empirical probability. It's not reason from first principles. That's the kind of the distinction. Questions here? Yeah. Well, if I just gave you a test question, right, that said, what's the probability a randomly chosen adult has a dog, you wouldn't be able to answer it. You would have to get some sort of data to kind of reason through it, right? So, and this wouldn't necessarily, unless you somehow went to all the dogs, this is an approximation, right? So if for some reason you didn't trust, so, right, like another example would be is if I rolled a dice many times, I wouldn't necessarily get a 2 exactly 1/6 of the time, right? So the number of times that the dice is rolled divided by, so the number of times I roll a 2 divided by the number of 2s I get would be the empirical probability. It's the probability that comes from actually doing the experiment. Does that distinction make sense? Okay. So again, yeah, empirical is like, so when they say you need empirical evidence of something, that means something that actually involves some sort of experiment. Okay, so why is probability important to statistics? So here's the law of large numbers, right? Roughly speaking, it says, right, this, right? If a procedure is repeated many times, the relative frequency probability, aka the empirical probability, tends to the actual probability, which they mean the theoretical. So just imagine rolling a dice, right? Like I was just talking about with Bob. So, right, if I roll a dice, say 6 times, I'm not guaranteed to get 1, 1, 1, 2, 1, 3, etc., right? If I roll it 60 times, right, I might not get exactly 6. I might not get exactly 10 ones, right? And if I roll it 600 times, I might not get exactly 100 ones, right? It might not be 1/6, but the more times I roll it, the closer on average, right, if I do this, that I'm going to get to the actual probability, right? So if I roll a dice 1,000 times, I'm more likely, my number, right, my proportion of how many of those rolls are sixes is close to be one, is going to be much closer to 1 out of 6 than if I do it just 10 or 11 times, right? Do we get kind of what this is saying? So the more times you do a procedure, the closer your empirical probability should get to your theoretical probability. Now, you want to be careful about what this does not mean. This applies to the behavior over a large number of trials. It does not apply to any one individual outcome. This is what I mean by that. While if you flip a coin many, many times, right? If you flip a coin 7 times, right? You could easily get something that's not very close to 1/2 of the outcomes being heads. If you flip it 700 times, it's much less likely, right? The more times you flip a coin, right, the probability over time will, the proportion of those coin flips that are heads should get really close to 1/2. But that does not mean this. Do not fall for the gambler's fallacy. The gambler's fallacy is, right, incorrect belief that if a particular event happens more frequently than normal in its past, it's less likely to happen in the future, or vice versa, right? So let's say I have a coin, and I know it's fair, right? Chance of getting a heads or a tails is 50%, right? I happen to flip the coin 10 times. Every time it's a heads, right? But you know the probability is 50-50, so you would say, okay, I am due for a tail, right? So you feel like it's more likely that that next flip is going to be a tail, right? Because I haven't been having enough tails. But the truth is, the probability that that next flip being a tail is 1 out of 2. It's always 1 out of 2, right? The coin doesn't remember what it flipped before, right? Even though this law of large numbers is true, it's saying, right, if you do a trial of so many, right, many times, it's more likely to be close to the actual fraction. It does not mean that if you're above that fraction, it's going to push the probability one way or another. This is called the gambler's fallacy. Others too, right? You're playing poker, right? I've lost so many hands, right? There's some skill in poker with the bluffing, but let's get rid of that, right? You know, I've been at this roulette machine. I keep pulling this lever, right? I've been winning less than I expected to by chance. So if I just keep playing, I'm more likely to win now, right? Because I need to bring it back down. Or, you know, it hasn't rained for a while, so I think we're due for rain tomorrow, right? These sorts of reasoning, right, are called the gambler's fallacy, because it incorrectly makes you think that each occurrence of the event affects the occurrence or the non-occurrence of the event the next time. All right, so I told you that there are 2 types of statistics. Right, we're doing probability right now. We're actually not doing statistics in this section so far, but I want to kind of help you see where it comes in. So I said there are 2 types of statistics, right? And you need to know one type to be able to do the second type, but the first type's not very interesting. The second type is very interesting. So the type of statistics you've been doing in all the 3 previous chapters were what type of statistics? Beginning with the letter D, that might be a hint. Descriptive, that's exactly right. Because remember, we were finding, I would give you a data set, right? What was pretty much all of chapter 3 is I give you this data set, you use something to describe it. You calculate its mode, its median, is it skewed, right? Whatever. That's descriptive statistics, right? So that's not that interesting because it only can tell you about a single data set, which you have right in front of you. The more interesting part is inferential statistics. What can I conclude about the population from a sample, right? So here is, roughly speaking, the rare event rule, right? Don't need to take a picture. This is where we're going to be going later, right? So yeah, this is kind of us getting the idea, right? So we might make an assumption, right? Do I have that on the next? What do I have here? No. Okay. So you have certain assumptions, right? If I have this dice, or if I have a coin, I assume the probability of it is when I flip it, I'll get heads 50% of the time, tails 50% of the time. Let's say I give you a coin, right? You're going to assume it's fair. But let's say I flip it 23 times and I get heads 20 times. What is our natural assumption? What's our natural thought if something like that happens? You all know this. I flip a coin 23 times. It comes up heads, let's say 22 times. It's rigged. So the assumption that the probability was 1/2, you're saying is to get heads is wrong, right? And why is that? Well, we can calculate the probability of getting, and we will do that later in this unit, of getting exactly 22 heads out of 23 flips, right? We can calculate that probability. It's very small. When an event, right, that has a very, right, but you're using an assumption. We're assuming if the coin is fair, the probability of something that we observed is very small, right? Well, something that has a probability of really small actually occurred. So there's either two things that could have happened. One, the coin was fair, and something just very unlikely happened. Things that are very unlikely do happen from time to time, right? Or our assumptions that we use to calculate that probability were false, right? The coin being rigged, right? So that's what in the rare rule event for inferential statistics. If an event under some given assumptions is extremely rare, and then that event actually occurs, our assumptions probably weren't correct. Now, what that threshold is different, right? How unlikely does it need to be for you to challenge your assumptions? Well, we don't know. This might seem a little strange, but they use 5%. That's not the best assumption, right? If you want to be more sure, you'd want to use something less than 5%, but that's this basic idea, right? So here's an example of that, right? And you want to usually look more or less, right? So let's say there is this pill that's supposedly supposed to make it more likely for a couple to have a girl. 100 couples take it, right? And it results in 75 girls, 25 boys, right? This is something that could happen by chance. Do we agree with this, right? Even if it was a 50-50 thing, this could happen, but it's not likely. You can calculate, and again, I'll teach you guys how to do this, right? You can calculate the probability of getting 75 or more girls. Here's the probability. It's 0.000003. That's so unlikely. Chance, right? The assumption of a 50-50 chance is rejected. So the solution method appears to be effective. Now, if you had 55 girls, okay, you could have that much. You would have that many 18% of the time. It's less than half, less than a third, but still not that unlikely. So that is not enough evidence to suggest the original assumption is wrong, right? So you don't have to really get this completely, right? But the idea is if something under certain assumptions is very unlikely, that thing actually occurs, you want to challenge your original assumptions, right? That's how inferential statistics work, and which is why you need to learn probability to be able to do inferential statistics. Questions? This will be easier once you have a method for doing this, but I'm just wanting to kind of give you a picture, right? This is just a preview of what is coming next. You may have heard the phrase odds instead of probability. I typically don't use the phrase odds, but maybe if you're involved in gambling, if you are of legal age, right, you might see that. So it's a ratio of two probabilities, right? I'm not going to talk much about it. I just want to give you the definition. So this is optimistic. If the Seahawks have 3-to-1 odds to win a particular game, that means that they are more than 3 times likely to win than lose, which really means the probability of them winning must be 3/4, and the probability of them losing is 1/4, right? So odds are always the probability of an event occurring divided by the probability of the event not occurring. And then you usually say it as a ratio. So in this case, 3/4. So odds can be 3-to-1 or 1-to-3. That's also a possible odd, right? But a probability is never, the first number is never more, right? The difference between odds and probabilities is odds compares the probability of an event occurring to its complement. Probability to compare is just the probability of an event occurring. Do we get the distinction? You can go backwards, right? If the odds of an event occurring are, let's say, like in this case, 3-to-1, well, then there are 3 ways for the event to occur, right? 1 way for the event not to occur, so the total number of ways is 4, 3/4. So if the odds of an event are occurring are m to n, the probability is m divided by m plus n. That's really all you need. And do this. Questions? I know I'm going through a lot. This is boring stuff. You'll practice it, right, on the assignment. I'll assign this to. Now would be a good time for your 5-minute break since we're between our sections. So let's take a break for 5 minutes. Try to stretch and get, yourself accustomed to what's going on, because we are going to start actually making things a little more interesting.